H2 set by default to be the? Okay, okay, so Thomas will, someone will put the button to get the sound from the recording. Okay.
I can actually grab. Just remind them to push the button before.
Yeah, that the green light comes on.
A couple of things.
Okay, so you'll go first. You have to remember to push this until the button turns green.
Okay, thanks. Do my best. I always think I'll remember it when I don't. But.
Okay.
Morning, everyone. Welcome to day 2. I hope you had a good, refreshing sleep so we can have a productive day. I just had a couple of things to touch base on. First, I've created Slack channels for each half day where I've posted all the presentations. I know some people were wondering about that. I cannot add everyone to the channels though, so you have to go look for the channel and add yourself in Slack. For the poster pops for today, I've also tagged the 6 people who are going to present. It's in the poster Slack channel. So go check there if you're a poster presenter. And then finally, we're going to take a group picture at the beginning of coffee break in the afternoon. So if you want to be in the picture, just be there. We'll probably go out front of the building. And with that, I'm going to let Charles Prophet here chair the first session.
Okay. First up is Kaylee Pittman, who will talk on the significance of HST to accretion studies in classical T polystars. 25 minutes.
Okay.
Probably waited.
Great. Okay, thanks, Charles. Is everyone able to hear me okay? Great. So my name's Kaylee Pittman. I'm a 4th-year PhD student at Boston University working with Catherine Espaillat. And today I'll be talking about the significance of HST to accretion studies in classical T Tauri stars using the Ulysses survey. So to start, giving the broad picture of accretion in T Tauri stars, which we've gotten great overviews already from Nuria and Carlo. But here's the first time you'll see this picture. You'll probably see it 15 times today. But just to go over the general picture, you have this central low mass star that has a really strong magnetic field. It's on the order of a kilogauss. This magnetic field is able to truncate the surrounding protoplanetary disk and funnel the inner disk material onto the star. So it's taking gas from the inner disk, flowing along, and then it shocks on the stellar surface. So my focus today will be on this accretion shock that forms just above the stellar photosphere. And this inner region is what is primarily probed by HST and the VLT. And we'll also hear about some hotline emission from Sonamuthanatibity today. And I'll be referencing some work by Kevin France on the inner disk H2 emission. So to start, here's an example of a Ulysses T Tauri star spectrum. This is using STIS low resolution spectra. So this is SY Cha, a K7, pretty typical accreting T Tauri star. And if we add in a non-accreting T Tauri star or a weak line T Tauri star, which is scaled by the measured continuum to the photospheric continuum, you can see that there is this very clear continuum excess that goes all the way from the NUV and it goes into the FUV, all the way out to the near infrared, where HST reaches its limit. So my work is to explain this continuum excess using accretion shock modeling. And so this continuum is coming from here, the accretion shock. So to go over the models I'm using, here's just another depiction of the system. So you have an inner gas disk and material flows along magnetic field lines onto the stellar surface, and this produces broad line emission. So Sometimes you'll see people model H alpha and H beta. That's coming from this part of the system. And then if you zoom in just above the stellar surface, this is where you have what we approximate as a one-dimensional accretion column. So you have this infalling flow that shocks at the stellar surface, produces X-ray emission that's absorbed and re-emitted in the ultraviolet and optical. And that's what we observe as this kind of accretion hotspot. So we know from 3D MHD modeling that the hotspot is not isothermal or uniform. It typically has some kind of density and temperature gradient. So to just build up the picture of the model that I'm specifically using, we start with a T-Tauri photosphere plus chromosphere. So this is just a non-accreting star of the same spectral type as our target star. We add on a hotspot with some non-isothermal structure. So the accretion flow that would cause this hotspot looks something like this. It has a given accretion rate and energy flux density F. And it's fairly complicated to model this as a continuous function. So we simplify it by using 3 accretion flows of different energy flux densities, which I'm calling the low, medium, and high energy flux density. So by fitting this model to the HST spectra, we're able to get 3 primary results. One is the percentage of the stellar surface that's covered by each accretion column. One is the mass accretion rate, both of the columns individually and the total mass accretion rate. And the other is an estimation of the extinction, which we call AV, the V-band extinction. So here's what these spectra actually look like. So spectra for the high, medium, and low energy flux density columns. You can see that the higher the energy is, the shorter the peak of the emission. So the highest energy emission peaks in the near ultraviolet, whereas the lowest energy emission peaks kind of near the near infrared. And I want to emphasize that all of this region that's shaded is not accessible from the ground because of the atmosphere. So if you want to know any information about this region of the system, you need to be able to observe from space. And just to show kind of the temperatures that are associated with this, this is just a simple black body fit to the spectra. You can see that the highest energy emission corresponds to about 11,000 Kelvin, whereas the lowest energy emission corresponds to about 4,400 Kelvin. So there's a pretty big temperature difference between these different energy flux density accretion columns. So I'm going to show an example of actually fitting these accretion shock models to the Ulysses data. So here again is SY Cha, the same star I showed earlier. And when we observe this, it is extincted by the interstellar material, so you need to do a correction for this. In reality, this is done at the same time as all the other fitting, but just to show kind of the effect this has, here is the correction for this. This one is not super heavily extincted, so the difference is pretty small. But the biggest differences are at the short wavelengths, because this is kind of the general shape of the accretion or the extinction function. So it's highest in the short wavelengths and lower at longer wavelengths. Once you correct for this, you can add in your non-accreting template photosphere chromosphere, which is the weak line T-Tauri star. And again, this is scaled by the measured veiling, contemporaneously measured veiling. And then you can add in the low energy flux density column calculated for this star's specific stellar parameters. And something I want to point out is that the slopes of these, especially in the optical, are fairly similar. And this is because the typical stellar temperature is about 4,000 Kelvin. And the temperature of this low energy flow is also about 4,000 Kelvin. So it's really important to fix the level of your template photosphere by your measured veiling, which is a separate and kind of more rigorous measurement of how much excess there actually is. It's important to fix that because otherwise you have a fairly significant degeneracy between these two model components. So just to see how these two are doing alone, here's a sum of these two model components. you can see that these two are able to take care of the longer wavelength excess pretty well, but there's still a lot of NUV excess emission missing. So then we can add in our medium energy flux density column. We're almost there. And then the high energy flux density column, and then you're able to explain the full continuum excess pretty well. And just to note here the filling factors for this. So this is the percentage of the stellar surface covered by each column. So generally, the low energy flux density column will cover a much larger surface than the high energy flux density column. So this is the difference between 23% and 0.01%. But you can see that the difference in the flux isn't that crazy. And again, just to emphasize the need for HST, much of this excess is only observable from space. So if you don't have Hubble or another UV space instrument, you don't know any information about what's happening here. So now I'm going to show my results from modeling the whole Ulysses T-Tauri star sample. And this is with Ulysses, or Odysseus and Penelope. So the procedure is first to get the data. So I use the Ulysses DR7 data release. This came out to 70 accreting Tauri stars from Taurus, Chameleon, Lupus, Orion, Corona Australis, and I put this all together into my sample. Then the Penelope team used the VLT X-shooter spectra to derive stellar parameters consistently across the whole sample. So the stellar radius, mass, and temperature are all inputs to the model to calculate the spectra. And then we measure contemporaneous failings using higher resolution spectra when possible. So that's VLT Espresso and UVES. And when those are insufficient, we use X-shooter. And then we calculate the accretion shock spectra for each star given its input stellar parameters, and then use an MCMC method to fit those spectra to the data. So here are my results. The accretion rates span 3 orders of magnitude, so it's a very broad range, but also within what we expect to see. Here's an example of the lowest accretor. So you can see that it has a very small excess in the UV, but almost no excess at longer wavelengths. So this corresponds to a filling factor of only 1%. So this is a very low accreting system, 3 times 10 to the minus 10 solar masses per year. Here's kind of an intermediate accretor. You can see it has a much stronger continuum excess. And then one of the higher accretors, it has a significantly larger continuum excess. So just to flip back, you can kind of see the difference that the continuum excess makes to the accretion rate measurement. I also find that for these targets in these, I think it's 7 different regions, all have extinction under about 1 magnitude, but I allow it to go up to 2 in the fitting. The hotspot coverage is usually under 10%. Based on previous work, I've restricted the total coverage to 40%, which I am open to discussion on that. But typically it is below 10% anyway. And this hotspot coverage, the high filling factors are dominated by the low energy emission. So it's not like you're having a super dense hot hotspot covering all the star. It's the lower energy emission that's more spread out. I'm finding that the medium energy flux density column is not that important in the fitting. I don't think it's just that the high and the low are totally sufficient. I think it has something to do with the kind of relative weirdness of the shape of the spectrum. This is something that is usually the case, so it's something I want to look into more. I think just kind of the irregularity of the spectrum makes it less likely to explain the more smooth continuum excesses that we see. And then the high energy flux density column always covers less than 5% of the solar surface as expected. So now going into kind of the main takeaways. So we observe diverse accretion column structures. This is a histogram showing the ratio or the percentage of the total accretion luminosity that comes from a given accretion column. So the blue is the lowest energy emission. You can see it kind of it's kind of all over. It can either be a very small percentage or a very large percentage of the total accretion luminosity. And that's the same for the high energy flux density column. It's just for the medium that it's usually not so important, but it still is sometimes significant. So here's an example of a fit that is dominated by the low energy emission in blue, one that's dominated by the medium, and one that's dominated by the high. So we see all of these cases. So it's not that it's always one column or another that's most important. It depends on the specific system you're looking at. Second result is that accretion column structures are poorly constrained by ground-based data. So I've done a test where I just ignore everything that's not available from space, but I fit the same data, just ignoring that. And here's an example showing how the model might look good in the optical, but it totally overestimates the NUV flux. And here's a case where it really underestimates the NUV flux. So this also isn't always in one direction. Thus far, there's no really clear correction factor that needs to be applied to change from the space-based result to the ground-based result, but this is something I'm still looking into. Third result is that extinction is also poorly constrained by ground-based data. So that's because you have this strong continuum kind of bump at 2175 angstroms. This is just an interstellar dust feature. And if you aren't including the short wavelength data, the model might find a better fit by increasing the extinction to fit the optical data, but it's clearly introduced just a spurious bump that's not physical. So when you do include the data, it looks more like this when you include the full range of the spectrum. Then I also find that the accretion luminosity is important for the inner disk chemistry. So this was work by Kevin France et al. On the y-axis is the emission, the radius from which the H2 emission is coming from in the inner disk. So that's looking here. And you measure this from the broadness of H2 emission lines in COS spectra. And they found a weak correlation between this emission radius of H2 and the luminosity of C4, which is an accretion tracer. So since I'm finding the full accretion luminosity, I wanted to see if I find this as well, because it's a more robust tracer than C4. And in fact, I do find an even stronger correlation. So this was a p-value of 0.4 and mine is of 0.5 of the emission radius versus the accretion luminosity. And I also find this for the H2 luminosity. So there is a clear correlation between the brightness of the accretion emission and the inner disk H2 emission. Fifth result is that accretion column structure might be important for inner disk chemistry. This is something that I'm still looking into. But I looked at the luminosities of the separate accretion columns. So they have peak brightnesses at different wavelengths, so the NUV, optical, or NIR. So here's for the low energy flux density column. So the luminosity of H2 on the y-axis and the luminosity of the low energy flux density column on the x-axis. P-value of 0.65 is a pretty significant correlation, decent correlation. Kind of as expected, I don't find a correlation with the medium energy flux density column just because it's not very significant in the fits in general. Usually it's just so low as to be not that important. But again, the weirdness of the spectrum. But I find the strongest correlation with the highest energy emission, which is what you expect because H2 is irradiated by ultraviolet emission. So you would expect the brightness of the H2 to be correlated with the brightness of the ultraviolet emission. And so this is a p-value of 0.75. So it is a stronger correlation with the highest energy emission, but it is still correlated with the low energy emission. So this is something very preliminary. I'm still looking into it, but yeah. And then the final result is that more analysis is needed of the stellar mass accretion rate relation. So just to build up what we kind of know from previous work, this is the relationship between the stellar mass and the accretion rate presented in Hartman et al. 2016, the accretion review. So this is the median and its standard deviations. So here are my results. You can see at the higher masses, it is pretty clearly in agreement. However, at the lower stellar masses, they only fall on the kind of upper limit of this relation. So something I want to look into is whether this gap is physical. I think Carlos suggested in the review that around 10 to the minus 10 solar masses per year accretion rate, there could be some like dissociation effect. But it also could be just for low mass stars, you're only able to observe the ones with more significant ultraviolet excesses because they're already so faint. So that's something I want to look into. Here's just coloring it by region age. You kind of expect the older regions to have stars with lower accretion rates just because of accretion rate evolution with time. And you can maybe see a little bit of like there are brighter, younger stars up here and maybe older ones, but it's not a really clear correlation there. And so if this is the real relation, it would give a much flatter relationship between mass and accretion rate. But again, that's really just driven by this gap here that I haven't determined the source of yet. So the next steps are to compare accretion rates to those of the Penelope team as well as the literature. So this is the first big Hubble accretion analysis that has been done. So I'm really interested to see how my results compare to those from the ground-based analysis that uses all of the same input stellar parameters. Like the only differences should be the data and the models. Then I want to explore the implications of the relationships with the inner disk H2 emission, and then determine the origin of that gap on the stellar mass accretion rate diagram. So this is really long, so I'll just leave the summary up, and I'm happy to take any questions.
Okay, do we have any questions in the room?
My name is Moritz Günther from MIT. I think this is great. I do have a question about why you have these different temperature components in the first place, though, because the material all comes falling in from the inner disk edge or from some relatively large distance to the star, and it's accelerated by gravity. So why is some of it gets hot and some of it stays cold, or is relatively cool? Then per unit of mass, it should have the same energy because it's just the gravitational energy that makes it fall in.
Yes, I'm not sure exactly. I mean, there are different densities. So I
Sure,
think
but per unit of mass, I mean, the gravitational energy is gmm over r squared. So per unit of mass, it's the same energy that gets freed. So where does that energy go for that material that comes in and is cooler?
Can I pass this to Nuria, who created the model?
The simple model that we have, sorry, this is just like an energy flux, and it's 1/2 rho v cubed. So we have like the velocity is the same, so it's got different densities. And in fact, the thing is that the flows, in fact, are very inhomogeneous, as we'll see in 2 talks, like Shawan has done like numerical calculations. So you see that, I mean, this is very simplistic, right? Because the only thing is probing is different densities, and this is something that is consistent with the simulations, right? But I think it's just right, but what I'm saying is that maybe we should ask.
Yeah, because this is a covering factor, right? It's a per unit area mass flux.
But the temperature you get also this per unit mass.
No.
Energy, you have the same energy per unit mass. In order to heat it up, you need 3 over 2
No,
K
no,
times 8.
Yeah, you have the the total energy you add is like rho v squared, right?
And the but
The-
the
if
energy
you
you need to heat it up is also rho. Also has a rho.
Effective temperature is opposite. Yeah, effective temperature.
Hmm? Yeah.
It's not okay.
Effective temperature.
Yeah, I just fit a black body to it kind of for fun.
Directly from the energy flux, like saying. You can calculate it from the energy flux yourself. The effective to the force is flux, right? That's what it.
I mean, this is all extremely nice, very well done. So I have a comment on the mass accretion stellar mass relation.
Mhm.
My fear here is that for the way, let's say STSI, but we all selected this sample, we wanted to detect the UV. So
Right.
we selected objects with accretion rates that were already known to be in this part. So my fear is that we are only seeing the tip of the iceberg here. So fitting it with the relation might not be a good description of the data for this reason. And what you miss is about half of the targets in a given subforming region. So I think this is just perfect, but simply we cannot use this to derive the relation, I think.
Yeah.
I have a question though, that's on the extinction.
Mhm.
So when exactly do you fit it? So is that iterative, or so you change the various aspects, the various filling factors, the various components with extinction
Right,
simultaneously?
at the same time.
Okay,
Mhm.
that's great.
Do we have any online questions?
Kat Barger, Texas Christian University. For the extinction part, I was wondering, is that the extinction that's mostly coming from the self-extinction from the region that is difficult to model? And is that also why you need space-based observation, I assume, because better angular resolution? Because it said specifically like ground-based are insufficient. So I was
Right.
thinking that space-based would be sufficient.
Yeah, so unfortunately, and this is something that we want to address, HSP panelists, we don't have great extinction as a function of wavelength determinations for all of the different regions, especially a lot of the ones in this sample. So my previous work found that a law determined specifically for the Taurus star-forming region applies well both to Taurus and to the Orion targets. And other kind of preliminary work that the general ISM law from Cardelli et al. 1989 works well enough for lupus, chameleon. So yeah, I'm not using extinction laws for each region, but that's, I would like to do better with that. And then the actual extinction value is just, whatever explains the excess the best.
Yeah, I'm just curious whether or not a different model would work better for different regions or not, just because they could have grains of different sizes in these regions. Yeah.
Yeah, it definitely would be. It would be great if we could have it towards each target.
Okay, thank you. Let's thank our speaker. And next up is Thanawu Thanabodi. I hope I did some justice to that name. Boston University, speaking about UV line modeling of T-Tauri stars and Ulysses observations.
Can everyone hear me okay? Good morning. So my name is Thanamut Thanatibodi. You can call me Atom if you want. My parents call me that. So yes, today I will show you some results of continuing in the accretion theme, modeling the UV hotlines in T-Tauri stars. So just to give you an overview, I will talk a little bit about magnetospheric accretion again and how that connects to the inner disk, and then review a little bit of what has been done about the hotlines in FUV spectra of this star. Then go into detail on how we create the model to connect all the pieces of accretions and how the carbon line or the FUV lines fit in that picture, and then some results. So protoplanetary disk set a stage for planet formation. So we have the disk. We have planets from somewhere in the disk. In the most region of the disk, we expect to see that Earth-like or rocky planets are forming, but that region is very hard to probe. So we like to probe that inner region of the disk. That inner region of the disk is directly connected to the star through magnetospheric accretion in T-Tauri star that Kelly and Nuria has already mentioned this figure for how many times, I don't know. But this is the original version without the chromosphere, but it's there, the chromosphere is there. So mass from the disk spiral into the star get truncated by the magnetosphere, magnetic field of the star at the truncation radius here, which would be important later, flow onto the star through accretion flow and create accretion shock. So in the accretion flow, we see the broad emission lines like the hydrogen-Balmer series and some helium lines perhaps. And at the accretion shock, we see the hot continuum emission that Kelly just mentioned, and also UV atomic lines. Now, when we zoom in, look at the FUV spectra that is observed by Hubble of a star, we see a forest of lines. Most of these are H2 molecular lines, and there are some very strong atomic emission lines like man alpha, carbon, helium, silicon, you know, all the your favorite lines. The question is, how do these lines form? But the bigger question is, why do we care? I mean, they're nice and bright and beautiful, but why should we care about them? First of all, a lot of these lines are related to accretion. This is the work from the DAO survey, which is a big HST survey before Ulysses many years ago, showing that the mass accretion rate is related to the luminosity of the carbon fluoride. So these lines are related to accretion. So we hope to use these lines to probe accretion properties. For example, if we can model them, we want to see the geometry of the accretion hotspot and also the structure of the accretion flow as well as the turbulence. And it can also, if we are lucky, give us an indirect probe of inner disk elemental abundance. If we can measure the abundance in the accretion flow, that is going to be the same elemental abundance as the inner disk of the star. If we can model these lines and give some abundance on that, that's the probe of the abundance. Also see a poster by Marbelli where she modeled the atomic lines in the accretion flow that is not hydrogen, and also get some abundance of that. So focus on the carbon 4 line. We have here one of the Ulysses stars, CVS 0107. Plot here, focus center, zero center at the lower wavelength line. So carbon 4 is a doublet. We can simply for the first pass, do a Gaussian decomposition. The left side, the blue side of the line has a H2 molecular emission. Each of these doublet has two components, so the narrow components, which is low velocity compared to the line center, and a broad component. So the narrow component, as I said, is low redshifted velocity. It looks kind of symmetric for most of the time. It could be coming from the post-shock region that Kelly just mentioned. For the broad component, it's high velocity, also mostly redshift. Mostly redshift compared to the line center, more redshifted than the narrow component, but some stars is not as redshifted. Some stars even have is blue shifted. So it could be coming from the pre-shock, which has high velocity, or magnetospheric flow, which could explain if it is blue shifted emission. But there are a variety of light profiles. So in most of the cases, or I would say all cases, the narrow components are redshifted. So the dashed line here is the line center, and the narrow component is redshifted for all of these. These are the 4 monitoring target stars, and I just picked one epoch out of many. Most of these stars have the narrow component velocity, peak velocity lower than the broad component. So GM Orica here and BP tau. It's clearer at the right side here. Some broad components are smooth, like GM Orica. You can fit it pretty well with a Gaussian or RU loop. Gaussian fits very well. Some are not as smooth. Some has some structure here, or TW Hydra. So how can we come up with a model to explain all this? Again, so we have this. We zoom in at the accretion shock. I'm not going to go into detail that much. We have pre-shock and post-shock heated photosphere. Some early models already have pre-shock and post-shock and calculate the line profile. This is 20 years ago. They use single velocity and single density flow, and then recalculate the post-shock structure and come up with a line profile. So in their model, the shock has uniform density. And it does show the narrow component and broad component at different, so this is angle of the hotspot from the pole, and it's different if the spot is big or small. But I mean, it's hard to model this, so it doesn't look that much like the observation. Also, I think this one is pretty close. So, but we know after that 20 years paper that accretion flow and spots are not uniform. There are multiple columns are needed to fit the spectra. Simulations and observations show that there is a density gradient in the hotspot. And so the flow is not, it's extended. So it comes from different truncation radii, which translate to different free fall velocity. So there's a velocity gradient in the accretion flow. If it's coming from further, it's flowing faster. If it's coming from closer to the star, it's flowing slower. The difference is not high, but it's on the order of tens of kilometers per second in the broad, in the pre-shock. So it could help to spread out the profile. So here, the attempt is to connect everything together. We have accretion shock model, accretion flow model, and it informs each other with mass accretion rate. And the truncation radius from fitting the flow model, and m dot and truncation radius filling factor give the geometry for the line modeling. Kelly go over this already, so I'll just skip. So the accretion flow model is from James Musro, who is here at Space Telescope, probably not in this room, but 20 years ago, he has this model where it's assumed very simplistically axisymmetric dipolar accretion flow. So it lands on the star as a ring and assume solar abundance in this flow and calculate the line profile of hydrogen. When we piece everything together, we have the, oh, it looks terrible in here, but we have the flow line here is zoomed in. We split all those 3 density flows into 5 columns. The inner one is the highest density and gradient out. And zoom in those, each of those columns, we have pre-shock, post-shock heated photosphere. So we assume that the models, the flow is axisymmetric. So you have a ring, and it lands radially on the surface, so there's no slant accretion flow. The large scale is ring, small scale, we assume plane parallel in calculating the line. And we assume for this model that the carbon 4 lines come from the pre-shock and post-shock. We set some free parameters, abundance, turbulent velocity. So here's the thermal and also atomic structures of the accretion flow. So from the shock model itself, it gives us for the pre-shock, the velocity and the density. So that's just a kinematic argument. And the post-shock, it calculates also the velocity, density, and temperature, which varies with the radius. So the pre-shock density is constant. The pre-shock speed is constant, and the temperature is calculated later by Cloudy, and we have the temperature structure. For the post-shock, the accretion shock model calculates these 3 parameters. And then this is used as an input into Cloudy to calculate the level population, ionization, and things like that for the carbon atom. And you can see it here. So carbon 4 is the red solid line. So carbon 4 is dominating the post-shock in a very narrow region. This is log centimeters. So 10 to the 2 to 10 to the 3 centimeter slab in the post-shock is where most of the carbon 4 is. In the pre-shock is a bigger slab. Here, 10 to the 7, 10 to the 8 centimeter. So the question is then, where does the life form? For the post-shock in the broad component, higher velocity is coming from the pre-shock. It's near the backside. So here's the source function and the opacity of the line opacity. So it's coming from where the source function peak here, and even though the opacity is not very high compared to the post-shock, the physical size is big, so it gets optically thick and gets self-absorbed. For the post-shock, the narrow component is coming from a very narrow region, the very narrow physical region. So it is optically thin and is coming from a region very close to the heated photosphere on the left here. So the velocity is not very high, like very, very low velocity. So now we assemble everything. The first thing is we look in the model and get the pieces. So this is different location, the emission from the different location on the star. So pick 3 locations. The post-shock emission does not care where is this in the star. It looks the same. The pre-shock has some velocity shift because you see different velocity if you look at the star at different angle. And also, this is one line, but it is self-absorbed at the center. Now, if we sum up all the emissions from the pre-shock and the post-shock for one accretion column across the star.
This is what
across the star, we can see that this is the total. So the dashed line here is the total. The pre-shock emission gets absorbed by the post-shock emission get absorbed by the wings of the pre-shock emission. So it's not as high as it should be. At some wing inclination, in some inclination it does not. So it has a very structured profile. And when we combine different accretion flows with different filling factors, we can see that the final profile. In this case, I assume the same filling factors. So you can see that the highest density flow, which is the green one, is the dominant one, while the lowest density flow, lowest energy flux, with the same filling factor, does not contribute much to the total line profile. So the broad component is the superposition of the absorbed line at different velocities, so it's kind of broadened out. The narrow components just sum up all this emission. So we have contemporaneous data from Ulysses and Penelope. So we have the observation, we have the filling factors from chalk modeling, we have the truncation radius from fitting the accretion flow in the optical Balmer lines, stellar parameters, and because everything is contemporaneous, we don't have to care about variability. Just a test object, this is the first set of the objects observed by Ulysses, so Orion, 5 million years. You can see all the different lines profile. And we fix a lot of things. We fix stellar parameters, filling factor inclination. We fix this truncation radii by fitting separately. And so in this model, we only measure vary turbulence and abundance. And I mean, inclination can be vary a little bit, but not by a lot, to try to see if we fix everything, can we fit it, anything at all? So density from density and filling factors from chalk modeling, truncation radius from fitting the Balmer lines here. The red is the fit, and the observation is the blue, so we can fit everything almost nicely, except some redshifted emission and some absorption features here that is probably coming from the winds or some other components. And so for Orion, we can fit 4 out of 7. So this 4 looks okay. This one is better than the others, but because of the gradients in and self-absorbed nature, it's kind of hard to fit the broad component. The lower part doesn't fit well at all. And so we can fit both the flux and the shape. And when looking into detail why we can't fit this, we see that this thing has large spot, very large spot. So there could be some other, the geometry effect of the actual geometry of the spot itself play into a role into determining the final line profile. When we retrieve the distribution of the parameters, we can see that the carbon abundance is lower than solar, and the turbulence velocity is high, around 50 kilometers per second in both post-shock and pre-shock. And they're comparable to carbon abundance measured by other method in the torus and TBU hydra region. So low carbon abundance is not a surprise result. And the reason why there could be lower carbon abundance is there could be dust trapping beyond the CO snow line, for example, the other explanation. We look at the monitoring target again. BP tau and G America is okay. This is H2 line, so it doesn't have to fit. We fit the narrow component, the broad component, hard as usual, but kind of tracing the geometry. RU loop and TW hydra just doesn't fit. These are low inclination also, and everything has big spots. So geometry effect play into a role here, and we assume a very simple geometry. So only the two started kind of fits okay. Because they're monitoring, we can plot it with with time. And we see that the carbon abundance is kind of stable. G America is a little less carbon depleted than BP tau. Turbulence are stable. Post-shock turbulence are stable across two epochs. So this is year 1 and year 2 across the days and months. There's no correlation with m dot with everything else. So the x-axis is the m dot and the y-axis are the model parameters here. So it's not like higher m dot, low abundance, or vice versa. It's just flat, well, mostly flat. So the question is, how much can we trust this abundance measurement? Well, the model is very constrained. We fix everything. So first of all, it's already hard to fit. So if it's fit, okay, it fits in that model. The line shape though depends a lot on the geometry. So because the bar component is optically thick, it depends a lot on what geometry you assume. The flux, especially at the narrow component, depends on the abundance. It doesn't really care where in the flow you are. And on the right side, I just plot one looking good star. The black is the observation, green is the best fit, and fix everything and varies the abundance. And you can see that abundance changed by half a dex, changed the flux by several orders of, well, yeah, an order of magnitude. So the flux level is what determines the carbon abundance here. So what we have learned so far is that the carbon line is profile strongly depends on the geometry. Abundance is important in fitting this, especially at setting the flux level. Some profiles fit better than the others, so the spot inclination and the geometry is important. So in future works, right now we assume something like this, like a donut shape. This is looking at the pole. But we see that in the simulation there's these other shapes that we can try. So that's future work. And then there are so many other lines in there that are related in the FUV spectra that are related to accretion. So it is cloudy, so we can get other parameters for other lines. And look at the whole sample. So just to summarize, we have a self-consistent modeling framework to model the carbon 4 line, carbon 4 doublet in T Tauri star. This ring light shock can reproduce about half of what we have looked at so far. And all of this, we see some evidence of carbon depletion. The level of actual depletion may be debatable, but everything is carbon depleted. So the turbulence here, I don't go into much detail, but all the turbulence fitting are at the order of 50 or more kilometers per second in both pre-shock and post-shock. So these accretion flows are very turbulent. And they don't change across many, many years. And so that's give more evidence that the carbon abundance we measure here is related to the inner disk, because they are not should not vary much across a larger time scale. And with that, I will take any question. Thank you very much.
Let's see, I think lots of questions, but I think you have your hand up first.
Yeah. Hello, nice talk. I was wondering about in these profiles that you mentioned that they don't fit because it may be like a geometrical effect. You showed some that fit very well and some that are too low or yeah, something like that. When you mention, for example, this low inclination, is because we know they are inclined, or we don't know and we're assuming that?
So this is TW Hydra and IU loop. We know that they are phase on. So, and we measure the the filling factor. So we know that half or some percentage of the surface is covered by the spot. But we don't really know the distribution of that. And so if we assume the ring structure and phase on, we would assume that all of the emission is coming from the same velocity because it's at the same ring, which make the lines kind of narrow, and that self-absorbed feature doesn't get spread out. For the lines at high inclination, you can see it at different angle more, so the lines spread out more.
Okay, and just to finish, to continue with that, yeah, you show that different geometries could be explored, but are these is this something that changes with time, or, for example, let's say you find for one spectra to be the middle picture that fits very well, but if you do another observation later, would that still be the case, or would you need to find another geometry?
I think that's the simulation tell us, I'm not very familiar with the simulation, but the simulation tell us that this shape probably live quite a while, probably not across the year, but within like the Ulysses short time observation epoch is probably one geometry should be constant. The geometry should be similar.
Okay. Thank you.
Greg Fink. I didn't understand here, because when you said you're going to carbon free, I thought, that's the thing I would fix, and I would vary the parameters. And then you showed that the carbon changed with time. So doesn't that mean there's something wrong? The carbon abundance won't change. That's almost a DEX, right? Oh, that's not time, that's m dot. Okay, so
yeah. Oh,
when you say it's constant,
with time
that's what
as
I didn't
well.
understand. I thought it was with time.
Yes, this one.
Yeah, so this almost varies by DEX with time. Surely that's not real.
Yes, they're not real. What it's saying is that the fitting is not, let's say, some profiles are fitting better than the others. That error bar is just for getting the first 100 best fits for each of those. I would say the values here are not absolute, and so it's just suggestive. And so,
wouldn't it be better to fix the carbon and to see what is actually physically changing with time?
That could be the things that we can try, because at first we don't know what values we should fix. Now, I guess now we know what value we should fix for each of those stars, and we can try. But in the first pass, we don't know what value we should fix that to. Because if we fix in the first, so this is like 2 years. In the first year, I fixed the carbon abundance to be solar and get the flux too high and never be able to get like the flux at the level that is comparable to observation.
That means you learn something about the deficiencies in your model or something. But I don't understand why you would. I just don't get it why you would vary the carbon abundance. Sorry.
One question back.
Yeah. Hi, Atom. Justin Campbell-White. Thank you for this talk. I had a question about the correlations between the line luminosities and the accretion luminosities. So I know Kaylee showed the plot for the carbon-4 line, and I just wondered if you knew or have any thought about the different components that you show for these highly complex lines, if some component should show stronger correlations with the accretion, or if these different profiles can explain some of the large spread that we see in those correlations.
So this profile coming out, okay, let's see if I understand your question correctly. So the question is, when I look at the profile and look at the contribution from each of the flows, which one is more important? Is that
Yeah, with the overall accretion luminosity.
more or less? From a quick look, I haven't really plot everything out, but from a quick look, it seems like there's a balance between the filling factor and the flux. And that balance ends up to be at the moderate accretion flow. So at the lowest accretion energy, it doesn't contribute much to the flux, even though it has, for same filling factor, even when you multiply that by 20, it's not going up very high. The highest density flows result in a very bright line, but the filling factor is very low. And so it's kind of balance it out. So I think that's also why it doesn't really correlate that with accretion here.
One
At
more
least for
very
a
quick
given
question.
time.
Quick question, yes. These are rapidly rotating, highly convective stars. They have stellar magnetic activity. What fraction of the low velocity narrow component can be from a stellar transition region?
Oh, I don't think I have a answer to that. So what I use here is that whatever the accretion model gives us and is assumed here. So some outer component is not taken into account.
The solar transition lines, I don't think are as strong as these ones.
Okay.
I don't think that the transition lines from the chromosphere are as strong as these. Some fraction can be. Not all.
Yes. Some fraction is in there, but I think I plot that. I didn't show it here, but I look into that, and it's a few percent of the total light. So if we assume that is compared with a weak T-Tauri star, and scale it with the distance and surface, is like a couple of percent in the light emission.
Yeah, we have a lot of discussion here. One,
Very quick question.
he had his hand up pretty early, so give him one very quick question.
Yeah,
and
so
then we have to move on.
So in your modeling, you mentioned self-absorption of the carbon-4. I'm just wondering when the proton, the excited electron, but also this electron also can be de-excited and emit the carbon-4 again. So why don't consider that component? Because this number density is too high. Is it collisionally de-excited, or just to simplify the model?
So where does that self-absorbed electron going to? So if we assume like the column, I think everything gets absorbed by the low density, the low temperature region at the back end of the flow. If that's answering your question, I'm not sure I understand it that.
Perhaps
well.
you can discuss that later in the coffee break then.
Thank you so much for the
Okay.
question.
Could the next speaker please thank
Thank
Anna
you.
Wood. Yeah. And you have to push the button and make sure the green light comes on. So, find your talk. You probably know this button, but it's a little arrow that should appear on the screen.
Right, thank you.
Should.
And, yeah, there it is. Okay.
Okay.
So thanks everyone for this talk. I'm actually going to be moving away from the accretion region. So the mission that I'm going to talk about here is more from the outer disk, and specifically from FUV heated winds. And that's sort of the broad topic of my talk. And this is actually it can actually span into a whole conference by itself. So I'm going to just going to giving you a little bit of what I think is important, especially from the Ulysses survey point of view. And so I will start with the motivation, and this is also really actually the takeaway that I want for you to at the end of the talk, which is basically that so the winds are central to disk evolution. So when I say winds, I mean the accretion that's actually that we've talked about so far in the previous two talks is materials being accreted from the outer disk. And this is now because we know the disks are not as ionized as we expect to be, and so therefore MRI turbulence doesn't work. And we think now that the dominant mode for accretion to happen is magnetohydrodynamic winds. And these winds sort of drive the entire disk evolution. So they bring material from the mass reservoir, which is in the outer part of the disk, to the inner part of the disk by losing angular momentum from the winds. And so to sort of dictate where material is present, because depending on where the winds are launched and how much mass loss is occurring at every radius, it sort of determines what the surface density distribution in the disk is going to be as a function of time. It tells you what the reservoirs available for planet formation are. And not only that, at later stages, we also expect that the winds actually disperse the disk. So these could be thermal or photoevaporative winds that get rid of the disk material and sort of result in the short few million year disk lifetimes that we have. And then therefore, they also dictate the time scale for planet formation and also where the reservoirs are for planet formation. So winds are basically central to all of disk evolution. And so now we want to know, it turns out that, as you'll find out soon, that we really don't know much about these winds, except that we see them sometimes. And so what's really critical is the line emission. That's it helps us determine what the mechanisms are, gives us an idea of what sort of mass loss occurs, where it occurs, for example. And then we sort of also get a handle on the disk densities and the temperatures, which is what we need. And so this is all available for us only from observing gas line emission. So that's sort of the motivation of the talk and also really the bottom line. And so I've called this, I've sort of have two sections. I've called this theory and models, but it's really a very brief description of where exactly all the data that we saw is going into a model. So I'm going to give you some idea of how I'm actually one of the end users of all the wonderful data that's come out. And so I will be sort of describing where I would like to use them and what sort of data is particularly relevant to the kinds of models that I do. And we've seen this plot, so I've sort of, I guess all of us are going to be showing this plot at some time or the other. And so the point here is that you have this accretion flow, and then you have UV coming out, as we just heard in the morning, and then so that sort of irradiates the surface of the disk. And they could be, and so when you're talking about heating the gas, what you really want are high energy photons. So this could be UV, this could be X-rays, or FUV photons. And that's sort of what the gas absorbs. It does not absorb anything much in the optical. So it's sort of these, if you want to directly heat the gas, that's kind of where you're going. And most of the disk surface, I'm going to say, is basically heated by FUV photons. And I'm talking about just the disk surface because remember the talks about emission from the winds and not really the disk as such. So I have here some sort of typical luminosities that are measured, and straight away you can see that FUV luminosities are pretty high. And the gas temperature as well is sort of are more in the few hundreds to a few thousand Kelvin. So here when I say X-rays, I'm predominantly talking about soft X-rays, which are softer X-rays, which sort of heat the surface of the disk. And then also you can see here, if you compare that, the FUV heats to deeper columns, depending on, of course, the dust properties in the wind, which sort of absorb some of the FUV. And the state of the gas is mostly atomic and molecular. So the main point that I want you to take away from this is that most of the surface of the disk is actually FUV heated. So that's sort of why we're interested in the FUV as such. And so this is the data that we have. So it's like, this is just from the Ulysses website. And so, we have this wonderful UV data. And so where exactly do we use it? And how does this help in heating the gas? This is sort of, I'll just give you a very brief one-slide overview of how FUV heating happens. Most of it is, so the most dominant mechanism is through dust, so which is sort of where the FUV heating is going. So what you have here are sort of three different, there it is, okay. So there's sort of three different dust sizes that I have here. So what's happening is that the mechanism is that you have an FUV photon. These are power molecules, and they hit the molecule, an electron gets ejected, and this electron has energy, which then collides with gas molecules and heats the gas. You can also do that for small grains, and for larger dust grains, you can sort of do the same thing. But in general, this process is more efficient for small grains for various reasons, because of the fact that this is really, you have to sort of overcome a work function, and so this is sort of this balance between ionization and recombination, and these processes depend on the area. So it turns out that it's easier to knock the electron off the smallest thing. So you have small grains, you're more efficient in heating. So that's sort of the primary mechanism by which FUV photons heat most of the disk gas. And then there is also pumping. So this is also a very dominant form of FUV heating. So what's happening here, for example, so this is a really old paper, but it's one of the earliest papers on this. So what's happening here, you're seeing the potential energy curves of hydrogen. So you have Lyman and Werner band photons, which sort of which get absorbed by a molecule in the ground excited state. It goes up to the higher excited electronic state. And then, so then there is radiative emission, a UV photon comes down, and then that sort of ends up in one of these vibrational levels, and then there's an energy cascade. So if you have optically thin gas, this can just cascade. You can sort of see that as your H2 infrared emission, which is often seen in disks. But then if you're in sort of a sufficiently dense region, then this energy then goes into heat. So this is sort of one way of heating, and this heating can actually be pretty dominant in winds as well, and especially in the surfaces of disks. And of course, what happens is that if you have if you have enough hydrogen column, if you're going up even further, then you can absorb these photons out. So H2 actually self-shields, because 90% of these photons sort of do this cascade, but 10% of them go into the dissociative state. So this is the primary way in which molecular hydrogen gets dissociated. And then you can sort of have you can sort of shield, H2 can shield itself if you have a sufficient column built up. And then in which case, what happens is that you sort of then lose the heating. And so as you go to deeper columns, you don't have as much heating. And of course, H2, many of you know, will also shield CO. So shielding of one species by another is particularly important, especially if they're all sort of competing for the same FUV photons. And so that is kind of what I've tried to show here. So this is a spectrum, courtesy Kaylee. We're modeling winds in DR Tau, which is a project I hope to complete, but we didn't sort of get to it before this conference. But so this is one of these model spectra of DR Tau in this case. And what I've shaded out here are different bands, because because of what I just said, that you can have photons that are absorbed by some species, which then shield other species. And so it's sort of important to worry about how these photons are propagating and what species you have in the interim, which are sort of absorbing these photons. It's sort of critical to understanding line emission in general. And so this is sort of a generic split that we do. So this is in our models, what we have is we sort of follow these discrete energy bins. They're very broad. I mean, Lyman alpha is the only one we sort of do in any detail, because this is actually complicated to do. But we sort of broke this up, and this breaking up is really based on dominant cross-sections. So dominant absorption cross-sections of different species. And I'm trying to give you a taste of that here. So what this is this is two such species which are sort of of interest in the disk. And okay, so this is the OH photodissociation rate, and this is the water photodissociation rate as a function of their column. And what you're looking at here is just some rate, but you can see that as the column increases, you can see that it also depends on the column of water. So in fact, if you have a lot of column of water along your line of sight, your photodissociation rate can decrease by orders of magnitude. And vice versa for water, so because OH can shield water as well. So if you have different columns of water, you can sort of shield water as well. So the main point I'm trying to make here is that the net rate depends on the photon flux in each bin. So you really have to worry about how these photons are propagating through the disk. And not only that, you also have, so some of this excess energy also goes into heating. So for example, if you have OH, you have a Lyman alpha photon, but you have only 7, you need only 7 EV to dissociate it, and you have excess energy. So this can then often goes into, let's say, producing OH in an excited state, and then it can cascade, collide down, and then sort of dump all this excess energy back into heat. So this is also a way of heating the gas, and so this can dominate in some regions, especially in regions like winds we're talking about, where there is less dust, because the winds are sort of blowing away. Dust often does not get entrained, and so that then means that you can have additional sources of heating. So it's important to sort of follow this, and this is kind of why I'm excited about the Ulysses data, because you have these spectra, and you can sort of integrate over cross sections, and you can sort of get these numbers in a more precise way. And so this is sort of where I would like to use most of the data, in fact. And so in the end, what I'm interested in, this is sort of what I do for my bread and butter. So I sort of construct these models of disks. So what you're looking at here is a model of a disk which is sort of has all the heating mechanisms and sort of solves for the temperature, density, structure in the disk with a lot of chemistry iterated over a whole bunch of things, which I'm not going to go into. But what I wanted to show you here is sort of the structure of the disk. So this is sort of an FUV irradiated disk. And these 4 panels here show you the disk structure. This is what you're looking at is the radius as a function of height, and this is sort of a slice through the disk. So you have, you can sort of determine what the densities are. This is the UV flux in these units, and these having units. It's some bin, I don't remember which one, but sort of shows you what the local UV flux looks like, and that's the dust and gas temperatures out here. And what you also get out of these models are these abundances. And this is sort of a typical, so this is H2, and this is the typical structure of a disk. You have an atomic layer on top. You have a molecular layer deeper in, where H goes to H2, and C goes from C plus to CO. There's a small sliver of atomic carbon here. And then as you go further down, you also have a freeze-out layer. So this is sort of where, for example, water is freezing out, and you can see that CO freezes out as well. So this is water ice. So this is the snow line, and you can see CO freezes out pretty close to that as well. And so there is also, UV is also important even at these depths, because much of the grain surface chemistry that happens on disks actually happens on these surfaces. And in fact, the layer of water ice is set by a photodesorption process where oxygen atoms are accreting onto grain surfaces and UV sort of dissolving the water ice back. I'm not going to get into that part of it because this is really a talk on disk winds. So we're only going to be dealing with the surface here. But I just wanted to point out that especially, for example, Lyman alpha is important in setting what the composition of material or dust grains and ices are, even in the interior of disks. So coming back to winds, so one of the things that I've worked on in the past is disk evolution through FeV photoevaporation, and that is partly motivated through a study such as these. So this is a plot from Fedele et al., and you can see here. So this was done a long time ago, but first by Lada and Lada back in 2001, I think. So what you're looking at here, I'm going to first draw your attention to this side of the plot. So this is age as a function of infrared excess. So this is these are different clusters. Each point is a cluster. And what you're looking at is the fraction of accreting stars observed here with IRAC. This is a Spitzer instrument, and you can see that they sort of decline with time. So the young clusters have a large fraction of disks, whereas the older ones have fewer fraction with an infrared excess. And what sort of Fedele showed in this plot is that if you look at the accretion rate, that also goes down very similarly with the dust, so sort of suggests that the gas and dust are dispersing simultaneously. And then, of course, also here you can sort of see the same plot, but that's so the interesting thing for me, at least with this, is sort of suggests that the gas and dust are dispersing simultaneously, and the best way I can think of doing that is via FUV, because it sort of produces both the accretion. So when the accretion dies down, the FUV dies down, and the disk goes away. So this is sort of a self-regulatory thing, and I've worked on this for many years, and this is actually a bad plot. I realized I should have plotted this in a different way, but I will try to walk you through this. So this is showing you the surface density evolution, so which is the evolution of a disk as a function of time and radius. So if you sort of cut a slice through, let's say, one of these, along the y-axis, what you're looking at is how the surface density declines with time. So this is kind of a snapshot way of looking at the entire disk evolution. So you can see that you start out, with some surface density distribution of the disk, which is like a really massive disk, and then as the disk evolves, it sort of then eventually disappears in a few million years. And what's causing this to happen is that you have mass loss rate driven by UV. So what's happening is that this is a purely thermal wind, so you're just sort of heating the surface of a disk, and you're causing these thermal winds to erode the disk eventually. So in the case of FUV, it turns out that you heat the outer part of the disk more effectively. So you can see that sort of prevents the disk from, it sort of shrinks the disk a little bit as the disk evolves. And you have most of the evolution is being driven from the outer disk. And then eventually what happens is that you get to the point where you are you sort of are removing material faster than it's accreting at some point. You drive a hole, and then the disk sort of disappears fast. And this is a viscously evolving disk, which is, I know, suspect, but that's sort of what we worked with initially. And so this is something I thought would be of interest to this particular audience. So this is a model where it was an exploration where what we did was we looked at disk evolution based on what the chromospheric luminosity of the FUV is. So remember, the FUV has two components. There is a accretion-driven component, which goes down as the disk goes away. So once there's no material to accrete, there is no accretion flow, and so the FUV dies down, if most of it stems from accretion. But then there's also a component that can come from the chromosphere. And if you have a high chromospheric accretion, then it turns out that you do open a gap. So sort of, for example, in later stages, you can see that if I draw a line through time, you'll see that there is no material in the inner part of the disk, and there's material in the outer part of the disk. And of course, if you have even higher chromospheric activity, this happens sooner, and you have a wide gap opening. But if you don't, then if it's very low activity, then it turns out that you don't open a gap, and this could be important for planet formation. So one of the things I'm interested in is sort of trying to figure out how much of the accretion comes from the chromosphere and how much of it comes from just pure accretion, and what that is as the disk evolves. So this is sort of something that I would like to look at. And of course, these models of ours are focused more on getting the temperature structure and the chemistry and solving for all of that, and then sort of doing dust evolution along with it, but did not really do the hydrodynamics of the flow, because we were interested in following the disk all the way until it disperses, and we thought that the flows are so subthermal that it's more important to get the temperature right. But there have been other approaches in the literature, so this is sort of newer models, which, this is by Komaki et al., and there have been others. So they sort of have the same thing, but now here what they do, they simplify considerably the treatment of temperature and the chemistry, and they also solve for the evolution only for a short period of time, but they do the full hydrodynamics. So the reassuring part of this is that, so this is what you're looking at, is a model. This is showing the gas temperature and the density and the flow velocities, and you can see over here that, I'm always losing this cursor. Yeah, so you can see here that this is the flow that's being launched from the surface of the disk, and so you have, ionized hydrogen, and then you have a neutral atomic flow, and then a molecular flow as well. And so the reassuring thing is that the numbers are sort of roughly right. Everybody gets about the same disk dispersal timescale, so it looks like this might be something that operates no matter how you do it. So this seems to be a fairly robust result. So this is sort of the applications of the FUV, in the sense that this is kind of all the questions that at least I'm interested in answering. How does the disk evolve? What does the emission tell you about the surface of the disk? What's the chemistry that's going on? And I hope that I've convinced you that sort of the FUV dominates most of these processes. And so I'll get to the second part of my talk, which is really more about trying to sort of see what we can already say about the line emission that we have seen. And so here is, I'm going to go through this fairly fast because I don't really have much to share here. But this is, for example, what we might expect from an ALMA observation of a photoevaporative wind. So it turns out this is, you can see here, this is a model that I created trying to figure out what the C1 emission would be, and was trying to observe this with ALMA. But you can see that there is actually very little. So the green curve here is a comparing disk with no wind, and the disk with the thermal wind only has like a slight wing, and so it's not even, it's not very easy to detect these winds. So that's sort of so it's not easy to detect the wind, at least from the cold outer part of the disk. But of course, we can see this from the inner part of the disk, and this has been done for years now, so starting with a study back in 1985 and with Hardigan et al., where they sort of observe these slow disk winds in forbidden lines. And here, these are sort of results from a very long project that I was on with Ilaria Pascucci and Susan Edwards for about 9 years. We looked at these forbidden lines from various objects, and we have like a whole bunch of papers that are devoted to this. And I was just going to highlight 2 of these. So this is a paper from Simon et al., where we sort of looked at these forbidden line profiles and broke them up into these low and narrow, low velocity and high velocity components, which are the jet and the wind, and then also broke this up into narrow and broad components. It's basically a Gaussian decomposition of the line structure. And we tried to analyze what we could, and what we find in general is that there are these slow winds, and then there are these, and they, not only that, they seem to be have these very specific sort of emission conditions. So this was examined in Fang et al. So we're looking at the line ratio here of the 5577 versus the 6300 and the similar S2 line with the O1 line. And sort of if you assume everything is thermal, it looks like there's a whole bunch of plots in here, I know, but the point of this is just to say that if it's all thermal, then it's consistent with high temperatures and high density. So this is sort of really difficult to get. And that's sort of one of the conclusions that we made. The other, another such result was by Andrea Banzatti, and what we concluded there was we found that both the narrow component and the broad component are correlated with the high velocity component, which is the jet. And the fact that they're both related sort of then suggests that this is really an MHD wind that we're seeing. This is what we think. And there's been the other lines of evidence, which I'm not going to go into. And we started out looking for photoevaporative winds, but then we concluded that most of this forbidden line emission that we see is really an MHD wind. And also shown here is another result that we had where we sort of did a spectroastrometric survey. Don't ask me anything about it. I think what we should look at really is this plot here. And so this data is apparently consistent with a wide-angled MHD wind. So this is sort of another way of looking at the same wind. And so we think that even spatially, this is sort of an extended wind that we're seeing. And yes, and so these are sort of failed attempts at modeling. So this is me. So there's a long history. What I've tried to do here is look at streamlined models, which is, sorry. So this is sort of not doing the whole modeling, but this is just sort of trying to impose streamlines on the disk, because this is a whole MHD disk, which is difficult to do consistently with the kind of chemistry and FUV excitation that you want to do. And so this is a structure where we've assumed some geometry and then try to solve for the temperature and the excitation and the line emission. And this is sort of one such attempt. So what you're looking at over here is the structure of the disk, the density, the gas, the flow velocity, and then various line emissions. In this case, I was looking at O1 lines, then the neon 2 line, and the S2 lines. So these are all lines that are seen. And then trying to reproduce, for example, given the surface density profile of mass loss, then what are the sort of emission line profiles that you can get? And there's there are many people who have done these sort of things. But the bottom line is that if you're trying to explain both the 5577 line, which requires higher excitation, has it's just overall pretty difficult to reproduce all of these lines simultaneously. So then what we're trying to do is, this is work in progress, but basically we're trying to see what additional forms of heating there can be. So we're looking specifically, because these are magnetic winds. So there is this postdoc, that Fulvio Pucci, who's working with Neil Turner at JPL, and what we're doing is trying to figure out if there are additional modes of heating which are possible, because this is a MHD-driven wind. And we find that this is promising, that this is a plot of the heating versus a height at some radius, and you can see that the reconnection heating could dominate. So we still have to figure out how exactly to fold this in with the chemistry, but it's a sort of work in progress. But at least it looks like there are additional heating mechanisms in the wind region that could perhaps bring the temperature up to what we need it to be. And there are other people who worked on this, obviously. I mean, this is sort of a very busy field. And so many people have actually, in fact, tried to reproduce the 016300 angstrom line, and this is two such results that I'm sort of showing here. There are many more. So this is a hydrodynamical model of a disk from Wang and Goodman. And recently there was a paper where Nibber and Goodman tried to use this model and Cloudy to sort of then explain the emission as being something via oxygen pumping. And then there's also been this work by Raab et al., for example, that we were trying to produce both the oxygen and the neon 2, this time from an X-ray heated photoevaporative wind. But I feel that based on all the work that we've done before, so my personal feeling is that you have to reproduce all the lines, because this looks like they're all correlated. And so it's really difficult to explain everything in this way, so which is sort of why I'm going the other route of trying to look for additional heating mechanisms. And so another thing that I want to sort of underscore here is that this is a model of an MHD model of heated wind. So these are the newest class of models where you're sort of doing this MHD simulations along with heating. So this was done with DALI by Oliver Gressel. And you can see here, so what I wanted to show you is that you have this velocity as a function of position along the streamline, and the wind base lies very near the FUV transition, so which then implies that whatever MHD wind you're launching, you're actually heating with FUV photons. And so that's sort of, I think, a very critical aspect of trying to figure out what the mass loss rate is going to be, because you have to sort of worry about, that sort of tells you where the wind base is, and that sort of tells you how much mass you're loading into the wind. And I think this is also something that underscores the need for doing FUV. And in that paper, they also sort of tried to come up with line profiles, which of course you would like to observe. That sort of tells you what the emitting conditions are. So in this case, they tried to predict what sort of line profiles you could have for different models. And you can see, of course, that the wind means that there is some asymmetry. There's like more blue emission, or there could be wind shift, or there could be shifts from the line emission, depending blue shifted emission, which also is indicative of a wind. And this is Newer results from JWST. I have 2 such slides. Please do not share this. I had permission from the PI to show this, but I think this is like really exciting, and this is sort of the new way forward. So what you're looking at over here are resolved winds. So this is an object which has a jet, and you can see that there is H2S9 wind, which is a line which is sort of clearly showing up in a conical wind. So you can actually spatially resolve these winds now. And the fact that it's molecular is sort of also telling you that this is a probably an FUV-driven, FUV heated wind at least. And this is most likely an MHD wind, but it's an FUV heated magnetic wind. And then there seems to be some indication of a wind in the CO fundamental line as well. Okay, so that is, I think, and then there's also, I'm not going to go into this, but this is sort of new work that we've been doing. This has been led by a student, by Naman Bajaj, who sort of you can see that we can actually detect now new lines of argon and neon, and which can also trace the winds. In this case, it's a spatially resolved neon 2 emission and argon emission. In this case, we think the argon is coming from EUV heated gas, and then the neon is probably coming from X-rays. And so this is also interesting because we can then use this to map out where the winds are coming from. And this is my concluding slide. I have no conclusions, but I thought I would end with this. So this sort of, it summarizes what I wanted to say, that ultraviolet radiation drives, okay, that's gone back. It's gone, okay. So anyway, that's, yeah, but you've also probably seen the plot. It's, I'm going to try to bring that back, yeah. But it's kind of cool, and it sort of, I think, summarizes or brings together the 2 different sort of fields in this conference, which is basically, in this case, what you're looking at is a photoevaporating disk in Orion, and this is H2 emission from it. So this made the cover of Science recently, and this is from the PDRs for All program, and you can see that this is, in this case, it's a low mass disk being heated by ultraviolet radiation from massive stars. So yeah, thank you very much.
Okay, we're up against the coffee break, but maybe we have time for one quick question.
So you showed that the neutral carbon line, you couldn't really see the difference in the line profiles, but for the externally photoevaporating stuff, you could sort of see the difference, not just in the line profiles, but in the position velocity diagrams. So is it too difficult for the internal FUV heated winds to see the difference between a disk and a wind in the position velocity diagrams?
Yeah, so what really happens in this case, it depends on how much carbon, how much neutral carbon you build up, at least in the models that I've done to date. What's happening is that so the wind is kind of fairly subthermal because you're sort of launching, it does not launch at a high speed because that's the sort of the launch speed. And the thermal, it's already cold gas. So you're really talking about very low velocities. So by the time the wind accelerates out, you're sort of coming to the point where you've dissociated CO. So you can't see CO, which would have been your best bet. And then very rapidly, the C1 layer is really a small sliver. So you haven't really accelerated the wind sufficiently enough. You'll probably see it in the C2, which is what will be nice, but we don't have C2. But that's sort of where you might expect the wind to have picked up. Because you sort of need a velocity shift, right? Which is hard with the C1, is at least what I've found as far as I've explored.
Okay, let's thank Uma and all our morning speakers. And schedule to resume at 11.